Hello everyone, welcome to our channel Clear and Concise.
Let's have a look at this question. The acceleration of simple harmonic motion of a pendulum is proportional to. The question clearly states that a pendulum is following simple harmonic motion. Simple harmonic motion is a to and fro oscillatory motion where the magnitude of restoring force F is directly proportional to the displacement x. Here, the negative sign signifies that restoring force always acts in the opposite direction to the displacement. We know force is equals to mass times acceleration. Substituting the same in above equation yields mass time acceleration is directly proportional to the displacement. So for the above question, acceleration is directly proportional to displacement. Option D is correct answer. Let's check whether the same holds true for pendulum or not. Let's consider a bob of mass m attached to the massless string of length L. Displace the mass by an angle of theta about its mean position. It starts oscillating across the arc about its mean position. So while it is oscillating, two forces will act on it. One is its self weight, another one is the tension in the string. So if we draw the free body diagram for that, we will be having weight which is equals to mass times gravitational constant mg which acts downwards and tension in the string T. If we resolve the weight along the axis of string and perpendicular to the axis of string, we will get mg cos theta and mg sin theta. Here the force mg sin theta pulls the mass towards its mean position. Now writing force balance for perpendicular axis yields minus mg sin theta equals to mx double dot, that is mass times acceleration. Mass gets cancelled. Assuming small displacements, that is if the angle theta is very small, then sin theta is approximately equals to theta. Substituting the same in above equation yields acceleration is equals to minus g theta. Rewriting this in terms of angular acceleration yields L theta double dot, that is length times angular acceleration equals to minus g theta. So here angular acceleration is equals to minus g by L theta. So we can say that angular acceleration is directly proportional to displacement and inversely proportional to length. So the correct answer is option D, displacement. It holds true for pendulum, spring mass system, shock absorbers and swings in the park. Whatever follows simple harmonic motion, it has to satisfy that acceleration should be directly proportional to displacement. Moving on to next question. Which are the following relationships between the force F on a particle and the particle's position x implies simple harmonic motion? From the previous question's discussion, we know that simple harmonic motion is an oscillatory motion where restoring force is directly proportional to the displacement. Here, if we observe the options, option A seems to be correct because it shows force is directly proportional to the displacement and it always acts in the opposite direction to the displacement. So F equals to minus 7x is the correct answer. If we observe other options where in option B force is equals to minus 200 x square, which is not true because it force is directly proportional to the displacement, not displacement square. Same holds for the option D. When it comes to option A and C, force is directly proportional to displacement, but in option A, force is directly proportional and it is acting opposite to the direction of displacement. So option A is correct answer. Let's solve this question. Speed of particle executing simple harmonic motion with amplitude A is half of the maximum speed. At that instant, displacement of the particle is. The question says a particle is executing simple harmonic motion and its amplitude is A and whose speed is half of the maximum speed. So at that particular instant, we have to find displacement. The displacement of particle executing simple harmonic motion is given by y equals to a sin omega t, where a is amplitude, y is displacement at any instant, omega is natural frequency and t is time. Now the velocity can be obtained by the derivative of displacement d by dt of y, which yields a omega cos omega t. Now maximum velocity is possible when cos theta is equals to 1. That is, when theta is 0, cos theta will be equals to 1 and the maximum velocity is a omega. In the problem, at one particular instant, the velocity of particle is half of the maximum velocity. That is a omega by 2. We need to find what is the angle at that particular instant. In order to do that, let's substitute particle velocity in general equation. So if we substitute that, we will get a omega by 2 equals to, so from this equation a omega by 2 equals to a omega cos omega t. We have to find omega t so that we can substitute the same in y equals to a sin omega t and get the displacement at that particular instant. So for that a omega gets cancelled both sides. Now cos omega t is half, where omega t will be pi by 3, that is 60 degrees. So cos 60 is 1 by 2. So now we will substitute this omega t in first equation. We will get y equals to a into sin pi by 3, that is root 3 by 2 a. Option B is correct answer. Thanks for watching this video. Please do subscribe to the channel for more interesting videos.